Hello everyone! Today we are going to talk about the ARP protocol. In this context, this protocol is actually what we call the Address Resolution Protocol. What does that mean? We've talked about this before. If a computer wants to send data to another, it has to go through multiple layers of encapsulation. For example, in this process, if my computer wants to access another computer, we need to use the ping command to access it. Now, this ping is not about sending some particularly powerful files or very important data to the other party. I just want to ask the other party if you can receive my message. Can you hear me? If yes, give me a reply. Then, what do we do? In any case, what is followed by the pin? The pin is followed by an IP address. If we first know the other party's IP address, then when we want to encapsulate it in the future, we also need a MAC address. Then in the future, we will encapsulate again. This source MAC address, I know this is my own destination. As for the MAC, can I know the other party's destination MAC in this process? I can't know it, because during our access process, I'm only pinging the IP address. However, later on, the MAC address is not included, so in this case, I am unable to complete data communication. At this point, our ARP protocol comes into play to assist me. The Address Resolution Protocol essentially means that I already know the other party's IP. I ask, what is your MAC address? Please tell me. The ARP can be said to be an indispensable protocol within our IPv4 protocol. It primarily helps us inquire about the other party's MAC address. Then after I ask, I can't just say, I know what your MAC address is. For example, here it might be 48A472 and so on. During this process, I can't say that today I find you once and ask you once. Then after 10 minutes, I ask you again. And after another 20 minutes, I ask for your MAC address again. Overall, the efficiency would be too low, so it stores the data it inquires into something called the ARP table. And then through the ARP table maintains the correspondence between our IP address and MAC address. In this process, besides this, of course, it has other advantages that we will discuss later. Now, for example, here, let's take a look. First, here our host A has an IP of 192.18.1.1. If in the future it wants to send some message to host B, what is the other party's IP address? This I already know, but I don't know the other party's MAC. So here I will send an ARP request. I will ask what is the MAC address of the host with IP address 192.168.1.2. If the other party receives it, they will send me an ARP reply which will record that. With the IP address, I am 192.168.1.2 and my MAC address is 48A4, etc., etc. This will be sent back to our host A so that in the future, host A can find it again. When our host B communicates, it will know what the other party's MAC address is. So how is this process implemented? Let's take a closer look. If, first of all, I send a broadcast packet here, and then wait for the other party's reply. Once I receive the reply, I will store it in the ARP table. Our network devices actually have an ARP cache table, or as we commonly call it, an ARP table. Inside it, there is a corresponding relationship between IP addresses and MAC addresses. Before sending data, it will first search this ARP table to see if there is an entry. If there is, then I don't need to ask again, because I already know the MAC address of the other party. If I find it, I will encapsulate this destination MAC address in my data packet, and then send the data to the other party. But if my table, doesn't have it, then my device will send an ARP request to find out what the MAC address of the other party actually is. In this context, the corresponding relationship between our IP address and MAC address, of course, won't be permanently stored in our ARP table. Within the validity period, our device can use this. The table searches for the target MAC address and then encapsulates it. At this point, you don't need to ask for the other party's MAC address because it's already in my table. However, if it expires, what happens to this table? It will be cleared and my table will have nothing in it. At that point, I will ask the other party again, what is your MAC address? And record it again in my table. During this process, if we now, I don't have it in my table, so how do I ask the other party? In this example, we can see that. We actually didn't have it earlier. Now let's say we need to ask. After that, I first just notice that my ARP table is empty. So at this point, I will send something called ARP request packet. Now you see the ARP request packet, the ARP protocol, actually operates between our network layer and data link layer. It doesn't belong to the network layer. But does it belong to the data link layer? Not exactly. It's more of an intermediate protocol. So, does it require complete encapsulation here? We often refer to it colloquially as a layer 2.5 protocol, which helps everyone understand it better. Here, it means that after generating data at layer 2.5, it still needs to go through layer 2 encapsulation, OS, before it can directly pass through the data link layer. After encapsulation, it goes through the physical layer for transmission. Is it necessary for me to first go through layer 4 encapsulation, then layer 3, then encapsulate my own data here, and finally layer 2? No, it's not necessary, because from its inception, it is already at layer 2.5. It's not a layer 4, so it doesn't need to encapsulate the original port, destination port, original IP, or destination IP. It only needs to be encapsulated from our layer 2. So for this type of protocol traffic, it's always like this. In other words, I directly generate the corresponding data, and then I can encapsulate it downwards, because this protocol traffic doesn't mean that. The traffic generated by US users, this protocol traffic, is to help our devices complete communication. It's not about saying, oh, I need to know how the other party's application is doing. That's not necessary. So in this process, we see that it encapsulates our header and trailer, meaning our original port, destination port, and FCS, frame check sequence, for error checking during this process. In this case, we can't find it in our ARP. So I encapsulate this ARP request information into the Ethernet data frame. In the header, the source MAC address is mine, which is the MAC address of my host. Do I know the destination MAC address here? Well, I definitely don't know. If I knew, I wouldn't be asking. So here, I want to know the other party's MAC address to the greatest extent possible. What should I do? I have to broadcast. The broadcast MAC address is FFF, which consists of 6 groups of F. Now, in this context, we are consolidating the address because broadcasting can reach everyone to the greatest extent as long as they are on the same local area network with me, which is the case here. The ARP request information contains the original MAC address, JOEC, and our target MAC address, which is broadcasted to our network. So, what does this ARP contain? It includes my data, and it specifies a type. I am the ARP request initiator, and during this process, my IP address, which means the sender's IP address, will also be recorded in this table as 192.168.1.1. So, whose MAC address am I looking for? What is the other party's IP address? The other party's IP address is 192.168.1.2. So during this process, we send the ARP request to the other party. Now, in this situation, it also needs to fill in the destination MAC, but I really don't know it. So here we use zeros as a placeholder, because I don't know it. For these unknown things, I replace them with zeros. Now, in this process, the broadcast I send will be received by any device connected to the same switch as me. It performs an action called flooding, which is similar to a flood. Any information received from my interface is sent out through all my other interfaces, so all devices will receive it. If the other side receives it, they will respond to me. Of course, if we have a device on our side as well. It is 192 point something, 192.168.1.3, so will it respond to me? It will not. This is like when we are in a network. For example, back when we were in school, if we had a pile of assignments in our hands that we needed to distribute to classmates in the class. But since it's a new class, we don't know which person corresponds to which classmate tool. So we can say, okay, who is Zhang-san? Where is your seat? Please tell me. If this person is Zhang-san, he will tell me, hey, I'm here. My seat is in the first row, second seat, to inform me of his position. But if this classmate is not Zhang-san, will he tell me? At this point, he won't tell me because he feels that I'm not looking for him. This is an ARP request. As for when we get to the response in the future, after receiving our ARP request information, each computer, including every device, will check the destination IP it carries to see if you're looking for it. Just go. If you're looking for it, it will check what its MAC address is and then send it to you. If not, it will ignore you. For example, my computer, let's say host 2. It will first take the sender's IP address from the ARP request information and the MAC address and put them into my cache table. Then I will proceed to send an ARP reply message back to the other party, because in the future, when I communicate with them, I need to know their IP and MAC addresses. Since you are looking for me, I will record it in my table. Now, if in this situation, our host 2 will reply to host 1 with an ARP response or reply message. In the ARP response information, what is the sender's IP address? It's my own. The sender's IP is my IP, which is 192.168.1.2. In this case, the recipient's MAC address is host 1's MAC, which is MAC 1. I know this MAC 1 because you just sent an ARP request message that included yours. The original MAC address, that is to say, host 1's MAC address, so I know it here, and also your previous ARP request packet. The packet also contains your IP address, so I also know who to send the future ARP reply packet to. In this case, do I still send it to the other party via broadcast? No, because only he wants to find me. So I will only send it to him. Now, in this case, he transmits it back in a unicast manner. What does unicast mean? Unicast means one-to-one, that is, only between two people. I only tell you my location. Now, in this process, after replying to our host 1, he will know which host I want to find in the future. What is the MAC address of host 2? Now, in this process, we say that after receiving our ARP response packet, host 1 will check whether the destination IP it carries is the destination of its message. In this case, it will record in my table, oh, I finally found 192.168.1.2, and your MAC address is this, and it will be generated in my table. So in the future, when I look for you again, I can freely communicate with you. When my aging time is up, for example, if our aging time is 20 minutes, after 20 minutes, do I immediately delete the message from the ARP cache table? It's not like that. For example, if we are friends and we're having a lively conversation, but then suddenly, after 20 minutes, I suddenly don't recognize you and you don't recognize me either. Is that possible? No, it's not. In this case, after 10 minutes, I will first send a unicast. I will first ask you, and if you reply to me, that's great. But if you don't reply, then after another 5 minutes, which means at the 15-minute mark, I will send another unicast to ask you if you're still okay, right? Are you still doing well? If you reply to me, that's certainly good. But if you don't reply after 10 minutes and still don't reply after 15 minutes, I will send a broadcast at the 20-minute mark to determine your status. Here, we should note that different systems have different default aging times, and you should make a judgment based on the system you are using. In this process, if we learn in the future, you might ask if ARP only has this one function. Actually, it doesn't. Besides using ARP to inquire about the other party's, let's say, MAC address, there are other uses as well. Another function is, for instance, when we send an ARP to communicate, I need to know the MAC address or schwa before sending an ARP. But here, what do we mean by a gratuitous ARP, like schwa? It's when I assign an IP address, like 192.168.1.1, to a device, it will send out this gratuitous ARP. So you might ask, why send this gratuitous ARP? It's to check if there is a duplicate address in the network. Suppose during this process, my address is 192.168.1.1, and in the same environment, someone else also has the address 1.1. If a PC3 comes along and tries to find 1.1, which host is it actually looking for, host 1 or host 2? It won't be able to distinguish. So during this process, we need to perform a check. What kind of check? It means I will send out a gratuitous ARP packet. When sending this gratuitous ARP packet, there are some things to pay attention to. At this time, our original IP and original MAC address are here. When we look at the original IP here, it is my IP1, and the destination IP also becomes IP1. In this case, my original MAC address is MAC1, but what about the destination MAC address? Is it still 000? What is the purpose of this packet? This packet initially sent as a gratuitous ARP packet. It is to ask if there is anyone in the environment called 192.168.111. If no one responds, then I know, oh, there is no one.